Well, greetings everyone. Welcome to another Martinized Mentoring Moment. Today's topic is going to be logarithms in real life with big number comparisons and examples. Caution, we have very serious nerd details ahead. There's going to be algebra and logarithms in here. Not a lot, but just enough to kind of tickle the fancy. A student came to me with a simple challenge. In his class, he had a summer class, he was writing a report. And they had a couple of numbers they wanted to compare, which are quite large. This number and that number, they wanted to compare them. Without using computers or calculators, show that 2 to the 309 power is approximately equal to or greater than 10 to the 93. Well, that was interesting. I hadn't thought about this in a long time, without calculators or computers. And I had to think back at what we used to do in the old days before we had all this cheap computation. Why and where do these big number comparisons pop up? Do they show up in counting? Oh, well, actually, no. Almost nowhere can you count to 10 to the 93. There's no ever situation where you would actually count it. The total number of atoms in the universe is, the observable universe, 14 billion light years, is less than 10 to the 85 power. So there's no way you could ever even, if you could count all the hydrogen atoms in the universe, there's no way you could even count that high. Combinations. Now, combinations are a different situation. They produce vastly different sets of numbers, and here's an example. Radio and TV station identifiers in the United States. Generally, radio and TV stations begin with a K or a W. Generally, W is for east of the Mississippi and K to the west. Originally, that was a setup. And then there are 3 letters after that. Well, these first 2 letters give you a choice. That's 2 possible choices, a K or a W. And then out here, ABC, ABD, ABE, ABF, blah, 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 all the way down to XYZ. Well, if you keep repeating that pattern, that's 26 to the 3 power. In other words, 26 letters, A, B, C, D, E, F, G, all the way to Z. Do it, and we can pick any one of those, and then we multiply by any other one. We do that 3 times, we get 26 to the 3 power, which is approximately 35,000. It's a little over 35,000. It gets 35,152 or something like that. It gets big fast. Here's another example where it gets big fast. Good computer passphrases. Good means long here. 407 years ago, our fathers brought, and it goes on, forth to this continent a new nation, Abraham Lincoln's Gettysburg Address. Key search space. This means if you actually had to search for this key in the blind and at random, just a bunch of monkeys typing on a keyboard, there's approximately 4.14 times 10 to the 92 possibilities to get there. In other words, you may have to test this many exactly. If you completely missed it, for sure half. There's a wonderful website from Gibson Security Research Corporation. How big is your haystack? In other words, searching for that needle in a haystack for your password. I encourage you to go look at this website and try out some of your passwords. Not the ones you're actually using, but ones that are similar or close. You'll discover very quickly that, it's fascinating what his theoretical calculations are for how quickly a password can be broken. So this is an example where big numbers show up. 10 to the 92, that's a lot. That's 1 with 92 zeros. My student came to me and was asking this question from a paper he was writing for a special summer project. It was called a transcomputational problem. Now, I had never heard of this, so I had to look it up. And it references something called Bremerman's limit from the Wikipedia page. In computational complexity theory, a transcomputational problem is a problem that requires processing of more than 10 to the 93 bits of information. That's a 1 with 93 zeros after it. Remember, there's not that many atoms in the universe as far as we know. I mean, that's the best estimate is less than that. It's 12 or 13 orders of magnitude lower, a trillion times smaller. Any number greater than 10 to the 93 is called a transcomputational number. The number 10 to the 93, called the Bremerman's limit, is the total number of bits processed by a hypothetical computer the size of the Earth within a time period equal to the estimated age of the Earth, approximately 4.5 billion years. The term transcomputational was coined by Bremerman, so I encourage you to go look at these Wikipedia pages, especially this one about Bremerman's limit where it discusses the power requirements of such a computer. In other words, there's probably not enough energy to actually run such a computer if it existed. So this is the size of the problem. Well, where does it show up? Well, the Wikipedia gives a very interesting example: testing integrated circuits. Exhaustively testing all combinations of an integrated circuit with 309 inputs. That means 309 wires going in. And one output requires testing of a total of 2 to the 309 power combinations of inputs. So what they're doing is they're wanting to put in a whole bunch of inputs and see if they get a good, bad result. Since the number 2 to the 309 is a transcomputational number, there's that phrase again, transcomputational. That is a number greater than 10 to the 93. The problem of testing such a system of integrated circuits is a transcomputational one. This means that there is no way one could verify the correctness of the circuit for all combinations of inputs through brute force flipping of bits alone. So the key idea here is, especially when you compare it to passwords, the same problem, long passwords are magic. Okay, let's flip down to the next slide and let's look at a circuit that might look like that. This is a symbolic diagram. Here we have a block of logic of some kind. Could be an exclusive OR gate, a NOR gate, any of those kind of like logic gates in TTL or CMOS electronics. Here you have 309 inputs, starting with 0, 308, so 300 plus one more is 309. All of these are yes, no, up and down, is 1 or 0 inputs. Then some mysterious but necessary logic happens and you get a yes or no output, good or bad, red or green. Well, where do these kind of problems actually occur? Of course, the Wikipedia says in computer circuits, but it also occurs surprisingly in other places like pumps on a pipeline. A pipeline is either pushing product or it's not. It's either moving material for oil and gas or water or it's not. And you can have a lot more than 309 pumps along a pipeline pushing the fluids up over hill and across dale and to get it thousands of miles from a source to a destination. Another place that this kind of a problem shows up is in a very large and complex building with the doors and windows, say for a security system. Doors closed, doors open. And there's some combination of these where, it's trivial combinations, all closed, so that would be a green, building is secure. All open, and it'll be red, building is not secure. But then, of course, there are other combinations where some doors are higher priority, and that's where this logic comes in. So like the door to the trash dumpster could be unlocked, and that would be okay because nobody could possibly crawl up the vertical shaft. But, the front door needs to be locked. And so there's all these kind of permutations and combinations in here of inputs. So in a large building, it's very possible to have this kind of an input and then just have a red or green output for the security watch. Conveyor belt systems, surprisingly in large warehouses and distribution facilities, or oftentimes in airports where there's like the Denverton Staple, and it used to be Staple, the Denverton International Airport, where they sort baggage. You have switches all over the place that are indicating gates closed or open for the conveyor belts. And so you can have a situation like this where you essentially get an output, yes or no, the system is working. Okay, let's move on to the next slide. Another real-life situation. This came up years ago indirectly in a neurobiology. This was helping an MCAT student, a medical comprehensive aptitude test student. The human brain has tens of thousands of nerve inputs. Matter of fact, according to the Wikipedia page, the average human being, about 1 inch of skin, has over 1,000 nerve endings. That means that your brain is essentially paying attention to thousands and thousands of nerve endings. Now, 1,000 is way bigger than 309. So why is your brain able to do this? And here's a classic example. Just standing up vertically and keeping your balance. Consider the vestibular system. This is your inner ear. Just to stay vertically balanced, your brain is listening to not only the little follicles and hairs in your inner ear and how your fluid level is, it's also monitoring muscle contractions. It's also looking at a visual horizon reference, and of course a differential tissue compression in your joints. So all this input goes pouring into your brain. Now, it actually doesn't completely all happen in your brain. Some of it happens in the backbone and some other places. There's some pre-processing that goes on before it gets to your brain. But basically, after all them inputs, What's the key feature? Are we balanced or not? Are we standing up or not? So it's not ridiculous to have situations where you have a lot of inputs and you just want to have a go or no go, a red or a green output. You have a lot of conditional inputs and then something come out. Well, this is a real problem. So my student was doing this problem, and it came up, well, how do you compare? Let's go back up here to what his challenge was. His comparison was, which is bigger, or are they approximately equal? 2 to the 309, 10 to the 93, because the Wikipedia page essentially, let's see if we can find that slide, makes that comparison. Since the number 2 to the 309 is a transcomputational problem, that is a number greater than 10 to the 93. So my student, his instructor challenged him, can he show a back of the envelope, pencil and paper, calculation of when is 2 to the 309 power approximately that. So we had to go back and review something called, in this case, logarithms. One of the ways to do this without computers is to do logarithms, and here's some algebraic steps to go with that. We start with the conditional equals. 2 to the 309 power is approximately equal to 10 to the 93. So this is a question we're going to test. If we take the logarithm base 10 of both sides, now we could have used any log base, but we're going to use the log 10 here. Log base 10, and there's a reason for using log base 10 because it'll make some parts of this pop out nice. Log base 10 of 2 to the 309 means that exponent in 309 can kind of roll back out here in the front. This is one of the properties of logarithms. And on the other side, we did log base 10 of 10 to the 93 power. That means the 93 can roll back out here in front, and we get log base 10 of 10, which is 1. Nice simple output. So we got 1 times 93 on this side. That's a very desirable thing to do. That gets us to something simpler. Now we have a little more tricky problem on the left-hand side. 309 times log base 10 of 2. Well, what is that? Well, that's a little trickier. So we have to examine 2 and ask ourselves, where is it at in the orders of magnitude? 2 is greater than 0 and is less than 10. And 10 is quite significant because 10 to the 1 power is 10. So in the exponential space, 2 is somewhere between 10 to the 0, which would actually be a 1. Should be, instead of 0 here, should be a 1. So 10 to the 0 is a 1. So 2 is going to be somewhere in here, and this exponent has to be found that will, some power of 10 will produce a 2 as an output. In other words, we raise 10 to some power, and we'll get 2 as an output. So what we're doing here is we're bracketing. We're looking at normal space, and we're bracketing in exponential space. Okay, or power of 10 space. So how do you get this power, how do you get this x without a computer or a calculator? Well, there are tables. National Bureau of Standards, United States National Bureau of Standards, lots of other places printed Napier's tables from the 1610s. Had a lot of tables. They are printed, common logarithm tables. You can look them up on the internet with a Google search, or you can find old books in bookstores. I think I actually have one somewhere. So you look in the table, and you look down here, and there's the number 2, and we don't have any decimal point, so it's 2.000. In other words, there's an implied decimal point in here. So 2.0, the log is 0.301. Now a little more approximate, it's 0.30103 if you go to 5 decimal places. And this table purports somehow out here that you can get to that 5th decimal place. Well, let's just take the table at its word. Use this. 2 is the log of 2 is 0.3010. We get this number here times 309. We do that multiplication, and we get 93.0179 is approximately equal to 93. Now remember, this is happening in exponent space. We've already taken the logs. Up here, log base 10 of 10 became 1, which was times 93. So that's what popped out on the right-hand side. So we have a very favorable comparison here, at least in the exponents, in the power of 10 space. If we back out to normal space and look at what comes out, we convert exponent space. We notice that, of course, that 93.0179 is greater than 93. If we convert those back to power of 10 in normal space, we get a bigger number. 2, that means this tells us that 2 to the 309 power is certainly bigger than 10 to the 93. So this is an example of using logarithms. Let's see if we can summarize here. This is an example of using logarithms to pop from normal space of big numbers, combinatorial huge numbers, do some comparisons in log space, and then pop back to normal space and get essentially a result of were they bigger, smaller, comparable, what were they? And there's a lot of background to this particular thing, but it was interesting because I thought it'd be interesting to bring this up because he was asking a tough question, and I hadn't thought about it in years about how to do this kind of a comparison without computers or calculators. As a matter of fact, in 20, 30 years ago, pocket calculators couldn't do these kind of calculations. They just didn't have, they were too small a mantissa and exponent. They would have a floating point error. Nowadays, it's nothing to do this. You can go to Google and do one of these calculations in the search bar. Well, that's it. Thank you for watching. Check back often for other episodes and other missives of Martinized mentoring moments. Take care and have a good day.